When we aim to answer causal questions, how should we go about collecting data? This question is a consideration of study designs. In this video, we'll connect the previously discussed notion of exchangeability to practical considerations about study designs. Recall that exchangeability is a fundamental assumption in causal inference. If exchangeability holds, this essentially means that the observed outcomes in the treated and untreated can be fairly compared, because the observed outcomes are a good representation of the missing potential outcomes. Exchangeability can hold in the full dataset, or may only hold within subsets of the data. These were the notions of marginal and conditional exchangeability. It would be nice if we could collect data in a way that either form would hold in our dataset. How can we? Let's take a look at some ways of designing studies to achieve exchangeability. Suppose that we're interested in understanding the causal effect of a new therapy for blood pressure as compared to an old therapy. In designing a study, there are a huge number of factors that are important to consider. These include enrollment and exclusion criteria, logistics of data collection and storage, ethics of study procedures, choice of measurement technologies, questionnaire design, just to name a few. While all of these are essential to think about in practical settings, we'll focus here on one aspect that is fundamentally important for causal inference, and that factor is treatment assignment. Treatment assignment has to do with decisions about who will receive the different versions of the treatment. In some settings, we do have the chance to be in complete control over who in our study will receive the different treatment versions. In the blood pressure example, how should we allocate the old versus the new therapy to study participants to ensure exchangeability of the treated and untreated? We should assign the treatment randomly. If we were only concerned about exchangeability and being able to accurately estimate the causal effect of the new therapy, randomized assignment helps prevent systematic differences between the treatment groups that would result in a lack of exchangeability. For example, exercise levels and fatty diet are two factors that could cause a lack of exchangeability. Low exercise and a high-fat diet generally cause higher blood pressure, and if either of these two characteristics is more prevalent in one of the treatment groups, exchangeability would not hold. Observed blood pressures in a low exercise, high-fat diet treatment group would be unfairly too high to accurately represent missing potential outcomes. And observed blood pressures in the higher exercise, lower fat diet group would be unfairly too low. We can view the effect of randomized treatment assignment graphically. The figure here shows the hypothetical distribution of potential blood pressures under treatment for all people in the study. Remember that we normally don't get to see this whole distribution. We wouldn't observe the part of the distribution corresponding to the untreated. Without random assignment, participants are left naturally to choose which therapy to use. And it could be that those who seek treatment are less healthy and have higher blood pressures in general. We can view this as a biased way to sample potential outcomes to observe. This biased sampling means that the observed blood pressures under the new therapy are misleadingly high. They're a poor way to fill in the missing treated potential outcomes in the untreated. When we randomly assign participants to treatment groups, we effectively draw a random, a representative, sample from the full distribution of potential outcomes. The observed outcomes are representative of the full distribution of potential outcomes. They fairly fill in the missing potential outcomes for the untreated. In other words, marginal exchangeability holds under randomized treatment assignment. These same ideas apply to the untreated potential outcome. It's important to emphasize that this representativeness of the observed outcomes is something that we expect, but is not guaranteed. It's entirely possible that the random number we use to randomly assign participants to the new or old therapy, just by chance, happens to put slightly older people in the new therapy group and slightly younger people in the old therapy group. In this case, despite the randomized assignment to treatment groups, the new and old therapy users are not comparable. One way to protect against these chance imbalances is to randomize treatment assignment within subsets of the study participants. For example, in groups defined by exercise levels. Within these groups, we could randomly assign participants to the new or old therapy. This results in conditional exchangeability because within the 3 subsets of the data, defined by these exercise levels, we would expect exchangeability to hold. That is, within those subsets, we can fairly compare the new and old therapy. Because exchangeability is expected in randomized experiments, they are viewed as the gold standard study design for causal inference, at least when experiments proceed according to plan. With randomized assignment, we expect exchangeability to hold, no matter the number of factors that could have driven systematic differences between the treatment groups. However, randomized experiments do not run perfectly in practice, and they're often riddled with ethical concerns. It's morally tenuous to randomize treatment when there's strong belief in certain courses of action being better than others. For this reason, we have to consider study designs other than randomized experiments to conduct causal inference in most settings. In thinking about a taxonomy of study designs, we essentially have experiments in one branch and non-experimental studies in the other branch. There are actually a very large variety of randomized experiments. We've only talked about 2 flavors: randomization of all study participants as a whole and randomization within subgroups. Other variations include designs such as crossover designs, where participants switch treatment groups partway through the experiment, and adaptive designs, where randomization decisions change and adapt as the study proceeds. Non-experimental studies are broadly called observational studies, so called because they entail observing study units passively without the chance to intervene on their lives. Because randomized experiments are the gold standard for causal inference, various types of observational studies try to replicate randomized treatment assignment as much as possible. These types of studies are often classified as quasi-experimental designs. We'll look at some examples of these designs shortly. Other types of observational studies will broadly be called general observational studies. Data sources for these studies can include databases of information, administrative records, surveys, or follow-up data collected from study subjects over time. Now, let's look at some quasi-experimental study designs. Randomized experiments use some sort of randomization device, nowadays usually computer random number generators, to randomly assign participants to treatment groups. In some situations, we're able to find things close to dice or random number generators naturally in the world. We're able to find some mechanism that essentially randomizes study units to treatment groups. Such a design is called an instrumental variables design. In an instrumental variables design, there's some variable called an instrument that we can essentially view as a random number generator, and this variable affects what treatment is received. Let's look at an example. A classic instrumental variable study looked at the effect of being a veteran on lifetime earnings. It's hard to conceive of veteran status in general as being randomly assigned, but the study's investigators did identify a clever instrument: the result of a war draft. In the Vietnam era, there was a draft lottery that essentially randomized individuals to be drafted or not. Individuals were assigned a random lottery number, and individuals with certain lottery numbers were drafted. Because there were other ways in which people could join the war besides the lottery draft, the lottery was not a perfect way of randomizing veteran status, but it came pretty close. This was still an observational study because investigators did no intervening on the study participants' lives. They just passively observed and collected data. We'll talk more about the instrumental variables approach in more detail later in the course, but for now, try to understand the motivation behind the study design by relating it to the goal of making exchangeability plausible. Another type of quasi-experimental study design is the regression discontinuity design. This design tries to emulate random assignment by using a cutoff on a quantitative variable to assign individuals to treatment groups. For example, a school may have scores on a pretest of students' reading ability. which we'll call C. The school may use a cutoff, say C0 equal to 50, to place students in a remedial reading program. The school's goal is to understand the causal effect of the remedial program on final test scores. The students with pre-test scores lower than the cutoff would be placed in the remedial program, A equal to 1, and those above the cutoff would not be placed in the program, A equals 0. Let's pretend for a second that there was no remedial reading program. The relationship between pre-test scores and final test scores, Y, is likely some positive association, as shown by the trend line here. But in the presence of the remedial program, those going through the program might experience real benefit and improve their test scores. For this reason, we might see a discontinuity in the trend at the cutoff. In a small region around the cutoff score of 50, the pre-test scores are essentially indistinguishable in terms of student ability. For example, a score of 49 likely represents no real difference in ability than a score of 51, but the student with a 49 goes through the remedial program, while the student with a 51 does not. Effectively, this means that in the small window of pre-test ability, pre-test scores essentially randomize students to receiving or not receiving remediation. We can then view the discontinuity as an estimate of the average causal effect of the treatment, specifically for the students in this small window of pre-test scores. As with the instrumental variables design, make sure that you can draw a connection between the motivation for this design and exchangeability. Related to the regression discontinuity design is the interrupted time series design. Here, there's an intervention that occurs at a certain point in time. For example, this could be a law regarding firearms that was put into effect in Minnesota in a certain year. The effect of the law on, say, rate of firearm homicides would be the main scientific interest. The hope in an interrupted time series design is that the timing of the intervention is random enough such that trends in the outcome over time are comparable just before and just after the intervention, and there's a sudden change in the outcome. If a discontinuity in the trend arises around the time of the intervention, we may be able to attribute that jump to the intervention. Making causal claims about differences in trends over time requires convincing analysis that other important factors also didn't change at the same time as the intervention. We can better think about those factors by analyzing time trends for control units. Here, for example, it would strengthen the analysis to have data on control states similar to Minnesota in key ways, but that did not enact the law. This would help us better understand what Minnesota's trends would have looked like in the absence of the law. To sum up this video, make sure that you understand how randomized treatment assignment relates to exchangeability and how the quasi-experimental designs that we discussed here try to imitate randomization. We'll visit these study designs in more detail at the statistical analysis level later in the course, but for now, our goal is just to have a sense for how we can use study design to intentionally set up situations where a key requirement for causal inference holds, exchangeability. Up next, we'll start learning about a very powerful tool for thinking through exchangeability and modeling data in causal settings, causal graphs. Causal graphs are very useful in thinking through and communicating about all of the study designs that we've discussed here, and they'll be a core theme in our course going forward.